to my channel. So today we are going to discuss the previous year's question papers of 2015 and 2014 for the Unit 1 Electrostatics. So this is a continuation of the segment Solve With Me. So first of all, we will discuss with 2015 where there were 4 questions, 1 mark question, a 3 mark question and a 5 mark question where there is an option for 5 mark question. So total weightage from the unit Electrostatics in 2015 was of 9 marks.
First question is a 1 mark question. Why do electrostatic field lines not form closed loop? The electric field lines does not form closed loops because it always starts from positive charge and ends in negative charge. So if there is no any negative charge near a positive charge, the electric field lines may ends in the infinity. So it always moves from positive to negative. It is always continuous. It cannot form a closed loop. Next is a 3 mark question. Calculate the potential difference and the energy stored in a capacitor C2 in the circuit shown in the figure. Given the potential at A is 90 volt, C1 is equal to 20 microfarad, C2 is equal to 30 microfarad and C3 is equal to 15 microfarad.
Second question is a 3 mark question where a circuit diagram is given in the question. So here is a circuit diagram. 3 capacitors C1, C2 and C3 are connected in series where C1 is of 30 microfarad, C2 is of 30 microfarad, C1 is of 20 microfarad, C2 is of 30 microfarad and C3 is of 15 microfarad. And the potential at A is also given. It is 90 volt. Here we have to find the potential and the energy stored in C2. So before finding the potential, first of all we will find the equivalent capacitance. In the series combination of capacitors, the equivalent capacitance of the reciprocal of equivalent capacitance will be sum of the reciprocal of individual capacitors. So here we will find the equivalent capacitance. 1 by C equivalent will be equal to 1 by C1 plus 1 by C2 plus 1 by C3. Just substituting the values for C1, C2 and C3, that is 20, 30 and 15. 1 by 20 plus 1 by 30 plus 1 by 15. In order to solve this, we will find the LCM. So the equation becomes 3 by 60 plus 2 by 60 plus 4 by 60. Where 3 plus 2 is 5, 5 plus 4 is 9. So the answer is 9 by 60 or 1 by the equivalent capacitance is 9 by 60. So the equivalent capacitance will be the reciprocal of 9 by 60. So here I can write C equivalent is equal to 1 by C equivalent is 9 by 60. So C equivalent is equal to 60 by 9 microfarad. So here we got an equivalent capacitance. In the series combination of the capacitors, since they are connected in series, the charge through C1, C2 and C3 will be seen. So now we will find the charge on C1, C2 and C3. All will be same. So in order to find the charge, here I am writing the equation Q is equal to CV. Instead of C, we can write it as 60 by 9 and instead of V, we can write it as 90 volt, where C is in microfarad. Here we have to convert it into farad. The microfarad is converting into farad, multiply with 10 raised to minus 6. And the volt is 90. The 9 and 90 cancel, so here we will be getting 10. So the answer is 600 into 10 raised to minus 6 coulomb. So this is a charge possessed by C1, C2 and C3. Now Q is equal to CV. From this equation, how we will obtain an equation for a potential? We can rearrange this equation. V will be equal to or V2 will be equal to Q divided by C2. We have to find the potential across C2. So V2 is equal to Q divided by C2. So instead of Q, we can write it as 600 into 10 raised to minus 6. Divided by, instead of C2 is nothing but 30 microfarad which is given in the question. So it is 30. Again the microfarad has to be converted into farad. So multiplying 10 raised to minus 6. 10 raised to minus 6, 10 raised to minus 6 cancels, and 30 and 600 cancels to get 20. So V2 is equal to 20 volt. The support potential across C2 is obtained as 20 volt. Now, we have to find the energy stored in C2. Equation for energy is half Q square divided by C2. We are going to find the energy stored in the second capacitor. So U is equal to half Q square by C2, or this is equal to half into, instead of Q we can write 600 into 10 raised to minus 6 the whole square, divided by C2 is 30 microfarad, again 30 into 10 raised to minus 6, or the equation become half into 600 into 600, because there is 600 square. The square of 10 raised to minus 6 is 10 raised to minus 12, divided by 30 into 10 raised to minus 6. 10 raised to minus 6 and 10 raised to minus 12 cancels to get 10 raised to minus 6 in the numerator. 30 and 600 cancels to get 20. 20 and 2 cancels. Now in the numerator it is 10. So 10 into 600 is 6000 into 10 power minus 6, or energy U is equal to 6 into 10 raised to minus 3 joules. We obtain the potential across the capacitance C2. V2 is equal to 20 volt, and the energy stored in C2, it is nothing but 6 into 10 raised to minus 3 joules.
Next is a 5-mark question. The A part is to define the electric flux and write its SI unit. Gauss law in electrostatics is true for any closed surface, no matter what its shape or size. Justify this statement with the help of a suitable diagram. Now comes the B part. Using Gauss law, prove that electric field inside a uniformly charged spherical shell is zero.
The first part is to define electric flux. So electric flux is nothing but it is a total number of electric field lines which is passing through an unit area cross section of a surface, or we can write flux phi is equal to E dot delta S, where delta S is the surface area of the closed surface. E is the electric field. The unit SI unit of electric flux is Newton meter square coulomb raised to minus 1. So this is the first part. In the second part, we have to prove that the electric flux only depends upon the charge enclosed by the surfaces with examples. So in order to prove that, here we will consider two surfaces. Okay. Let this be the surface number 1 and let this be the surface number 2. It is clear from the figure that both the surfaces are different in size as well as different in shape. Both are having different size as well as shape. But let both enclosures equal charges. I mean the charge enclosed by the surface 1 and surface 2 are having same magnitude. So how we will find the electric flux through surface 1 and 2? It is obviously by Gauss law. So here we will use Gauss law. According to Gauss law, the flux through a closed surface is equal to 1 by epsilon 0 times the charge enclosed by that surface. So we will find the flux through the surface 1. Let it be phi 1. So phi 1 is equal to 1 by epsilon 0 times the charge enclosed by the surface, where charge enclosed by the surface is Q. So I got the equation for phi 1. Let this be equation number 1. Similarly, we will find the flux through the second surface. Let it be phi 2. Again, according to the Gauss law, it is 1 by epsilon 0 times the charge enclosed by the second surface. Again, it is 1 by epsilon 0 Q. Let this be equation number 2. Comparing 1 and 2, we can say that phi 1 is equal to phi 2. So, irrespective of its size and shape, the flux through the surfaces are same. Why? Because the electric flux only depends upon the electric flux only depends upon the charge enclosed by the surface. It never depends upon the size or shape of the surface. Whatever size or whatever shape, if the charges enclosing by the surfaces are same magnitude, then the electric flux passing through that surfaces will be equal. Now comes the third part, or the second part of the question, is to find the electric field due to a spherical shell outside, inside and on the shell, which is excluded from this academic year 2020.
Next is the option for the essay. The first part is to derive the expression for energy stored in a parallel plate capacitor and hence obtain the expression for energy density of the electric field. Now comes the B part. A fully charged parallel plate capacitor is connected across another uncharged capacitor. Show that energy stored in the combination is less than that of in the initial case.
The first part of the choice is to derive the expression for energy stored in a capacitor. For that you can check the description box where there is a detailed video. Now we have to find the energy density. So energy density, I am representing energy density as capital U. Energy density is nothing but energy divided by volume or energy per volume. Now, if A is the area of the parallel plate and D is the thickness of the plate, then definitely volume will be equal to A into D, area into the thickness. Similarly, equation for energy is half CV square or half Q square by C. You can use any equation. So we will substitute these equations in the equation of energy density. So U becomes half CV square divided by volume V. Instead of volume V, we can write it as AD, or it is CV square divided by 2AD. Okay, where we can write C as epsilon 0 A divided by D. This is a derivation of capacitance of a parallel plate capacitance without dielectric. You can check the description box for the detailed video how to derive C is equal to epsilon 0 A divided by D. Similarly, potential V is nothing but E into D, where E is the electric field. Now the electric field in between the parallel plates of a capacitor is equal to sigma by epsilon 0. So V can be written as sigma by epsilon 0 D. So the equation for C and equation for V can be substituted in the equation for energy density. Instead of C, we can substitute epsilon 0 A divided by D, and instead of V, we can substitute sigma by epsilon 0 D. So here U is equal to epsilon 0 A by D. Instead of V square, we can write sigma by epsilon 0 D into sigma by epsilon 0 D. And in the denominator, there is 2AD. So 2A into D. Okay, where A cancels, 1D cancels, epsilon 0 cancels. So again, there is a D, D cancels. So U is equal to, denominator there is sigma square, divided by, in numerator there is 2 epsilon 0. This is the energy density in the electric field or energy density in between the parallel plate capacitor, sigma square by 2 epsilon 0, where sigma can be replaced as Q divided by A, or else you can write this equation in the terms of sigma, that is energy density U is equal to sigma square divided by 2 epsilon 0. So this is how we derive the energy density in between the parallel plate capacitor or in the electric field. In the second part of the question, we have a fully charged capacitor. Let it be C1. Potential differences across C is V. So we will find the energy U1 is equal to half CV square. Now we are connecting another capacitance, a similar capacitance across this capacitor. Since the capacitor is similar, the capacitance will be C. Both the capacitance are equal. So when such an uncharged capacitor is connected across a charged capacitor, the charges gets distributed until the charge in each capacitance becomes equal. So if initially the charge is Q, it gets distributed until both the capacitors possess equal charges. That means the charge on both the capacitance becomes Q by 2. Similarly, the charge distribution continues until the potential becomes equal. So if initially the potential is V, the process of charge distribution continues until the V becomes V by 2, or the potential differences across both the capacitors becomes same, that is V by 2. So after connecting an uncharged capacitor, the potential across both the capacitance will be same, that is V by 2. The charge distribution continues until the potential becomes same. So here we will find the energy of this combination. Energy stored in the combination of a capacitor is nothing but the sum of individual energies. So first of all, we will find the energy stored in the first capacitor. It is half into C into V by 2 the whole square. Now the potential difference across the first capacitor is V by 2 plus half into across the second capacitor. Again it is C into V by 2 the whole square. Or I can write this equation as half into 2 into CV by 2 the whole square, where 2 cancels, or we can write U2 as half CV or 1 by 4 CV square, because 2 square is 4, so 1 by 4 CV square. So we got U2. So here comparing U1 and U2, U1 is equal to half CV square, U2 is equal to 1 by 4 CV square. From this equation, it is clear that U2 is less than U1, or we will find the ratio U1 by U2 is nothing but 2:1. So thus we find, or thus we prove that U2 is less than U1. U2 is 1 by 2 times U1, or U1 by U2, or U1 is to U2 is nothing but 2:1. In 2014, there were 3 questions. A 1 mark question, a 2 mark question and a 5 mark question, where there was a choice for 5 mark question. So the total weightage in the year 2014 from grade 1 electrostatics is of 8 marks.
So here is the first question of 1 mark. What is the force between two small charges of 2 into 10 raised to minus 7 coulomb placed at 30 centimeter apart in the air?
First question is a 1 mark question, which is an easy problem. We can directly substitute the given quantities in the equation and find the answer. So this is a question where two charges Q1 and Q2, which are equal in magnitude. The magnitude is also given. It is 2 into 10 raised to minus 7. Is separated by a small distance 30 centimeter. We have to find the force experienced by Q1 and Q2. So according to Coulomb's law, the force experienced by two charges which are separated by a small distance r is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r square. So we will write the equation. F is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r square. Instead of 1 by 4 pi epsilon 0, we can write 9 into 10 raised to minus 9. Instead of q1, 2 into 10 raised to minus 7, which is given in the question. Instead of Q2, the charges are of same magnitude. Again 2 into 10 raised to minus 7. Instead of R, it is 30 centimeter. Here, we have to convert centimeter into meter. So, 30 into 10 raised to minus 2 the whole square. Solving this, we will be getting the answer as 4 into 10 raised to minus 3. Force as Newton. So directly substituting the values to the equation, that is for Coulomb's law, we will be getting the answer for force experienced by Q1 and Q2. It is 4 into 10 raised to minus 3 Newton.
2 mark question. A parallel plate capacitor of capacitance C is charged to a potential V. It is then connected to another uncharged capacitor with the same capacitance. Find out the ratio of energy stored in the combined system to the energy stored initially in the single capacitor.
This question is the same question as we discussed in the previous year, that is in the year 2015, the second part of the last essay that we discussed. So for answer, please rewind.
Here is the essay question where the first question is to draw the label diagram of Van de Graaff generator, which is excluded from the syllabus. Now we will discuss the old question where the first part is to deduce the expression for torque acting on a dipole of dipole moment P in the presence of a uniform electric field. Consider two hollow concentric spheres S1 and S2 and closing the charges 2q and 4q respectively. Find the ratio of flux passing through it.
The first essay is about Van de Graaff generator, which is excluded from your syllabus. And in the second essay, in the old question, the first part is to derive the expression for torque experienced by an electric dipole which is kept in a uniform electric field, where we did a detailed video, detailed derivation in the last segment of the Solve With Me. So you can check the description box for the link. In the second part, there are two surfaces S1 and S2. Here is a figure. The figure is given in the question. where S1 encloses a charge of 2Q and S2 is enclosing the charge 4Q plus 2Q, or S2 is enclosing the charge 4Q. Now, we have to find the ratio of the flux passing through S1 and S2. So, first of all, we will find the flux passing through S1. Let it be phi 1. According to Gauss theorem, the flux passing through a closed surface is 1 by epsilon 0 times the charge enclosed by that surface. So, if you are considering S1, the charge enclosed by S1 is 2Q. So, I can write phi 1 as 1 by epsilon 0 into 2Q, because 2 charge enclosed by S1. Similarly, we will find the flux passing through S2, let it be phi 2, which is equal to 1 epsilon 0 into the charge enclosed by S2. Actually, S2 encloses 4Q as well as 2Q. The 4Q and 2Q are inside S2. So, the total charge enclosing S2 is 4Q plus 2Q. Or I can write this equation as 1 by epsilon 0 6Q. 4Q plus 2Q is 6Q. Let this equation be 1, 2 and phi 1 is 1. To find the ratio, we will divide 1 and 2. So, phi 1 by phi 2 is equal to 1 by epsilon 0 2Q divided by 1 by epsilon 0 6Q, where 1 by epsilon 0 is common, Q is common, so it is 2 by 6 or 1 by 3. So, phi 1 is to phi 2. The flux passing through S1 is to flux passing through S2 is nothing but 1 is to 3. So, thus we found the ratio of the flux passing through S1 and S2 in the case of this figure. So, that's all for today. In this segment, we discussed 2015 and 2014 board papers of the unit Electrostatics. So if you find this video helpful, please don't forget to subscribe, share and like my channel. So we will see you soon, and thank you for watching me.